Okay guys, welcome back to our StreeterPhelps modeling exercise. We're now going to look at the next phase, which will actually be phase 3, or actually phase 4, developing the model and then creating time steps of the basic StreeterPhelps model. So we're not going to bring sediment oxygen demand or any non-point source oxygen demand into the model at this stage, but we're just going to look at creating those time steps. We've already set our initial boundaries, and this is our next step. So if we go to Excel, let's have a look at Excel. You should have something like this, or basically what I've seen in your homework is this is what you have. The next step then is to go ahead and look at the next cells in that time step. It's fairly elementary once you kind of get hold of it, but it just takes a little bit of work. So our time step for the first one, for instance, we would go in this next, our time at t equals 0 is of course 0. So our next time step would be t equals 0 plus this guy over here, our time step. So let's have a look at that. We want to make sure that we always refer to B9 because it's a constant and not a variable. It doesn't vary by cell. So let's make sure that B9 is anchored with those dollar signs. And then what we can do is you can drag and drop this. Now if I want to change my time step, watch what happens if I change this from 0.1 say to a 1. Now all of a sudden my time steps are different. So that helps us in the process, and if you look, your time steps are also your constants based on your time step should change as well. So that's one of your first things that you do. You make sure that that time step is ready, and you can then vary your time step if you want to do that in the model. The second part is the remaining UOD. So basically I can't always remember what formula, not that it's a particularly difficult formula, but I went to the PowerPoint slide, and it says our L, our remaining UOD at t plus 1 is L at t. Okay, in this case t plus 1 is at 0.1, and t would be at t equals 0. Would be L at t minus KDL times, and that all times delta t. Now because our KD has already been factored in a delta t step, we don't have to worry about that, including that delta t factor in. So our remaining L now is fairly simple. It's equals, this L is over there, L at t, which would be 8.8, minus K times D, KD times L, and that would be at t equals 0, or at the previous time step. And when you do that, you come up with this number. Let's just go ahead and reduce that a little bit. You can see now my L has actually dropped a little bit. My UOD has been consumed in that situation. So that's all that you need for UOD. Let's go to DO. Our DO at t equals our re-aeration. First of all, we add our re-aeration factor, which is this one over here, KRD, which would be KRCS minus C. And then, so you'd add that factor, but you'd subtract this factor, which is fairly simple. So our DO is C at t. You add KRD, and you subtract KDL. Okay, that's because that's the BOD being consumed. What's it consuming? It's consuming the DO. And so in both cases now what you find is both your UOD goes down and your DO goes down. So if you think about it logically, your UOD is being consumed by the DO in that bacterial or microbial process, plus your DO is being consumed. But you'll notice that your DO will not be consumed at the same rate because there's some re-aeration. So that makes sense. Okay. The next, in both of these, you're not anchoring either of them. Those are variables. They depend on everything within this area. So it's a variable based on your time steps. Your difference between saturated and your regular dissolved oxygen, that is going to be the same formula, but I'm just going to go through it again, is equal to, where's my saturated DO, is over here. And we remember that's a constant. So we just want to put those dollar signs in there. If you don't put the dollar signs in, you may find you're going to run into a lot of trouble. Now we know what our actual DO is already. It's right here, at time equals t plus 1. So we've got that. Okay, that's let's go ahead. And so in fact, the difference between DO saturated and actual DO now goes up a little bit because our actual DO has gone down by that same amount. So that makes sense as well. All right. KDL now, it's also the same really as this formula, but let's do that again. So we know KD for a delta time step is 0.015 in this case. We want to make sure we anchor that so it doesn't run as a variable, but we multiply it in this case by our D over here. Now that D is going to be a variable, so we're not going to anchor it. And in the same token, let's just do that. In the same token, we're going to do the same thing. KRD is going to be KR. There's my re-aeration rate times my difference between C. Okay, let's make sure we anchor that first. Oh. Yes. Okay, so let's just make sure that that's correct. Now B45 less the difference. Sorry, not less. B45 times this difference. And boom, we've got that. Now, all we need to do is drag and drop this, or I use Control and D, and we can sort of run this down the line and see whether we've got something that actually works. Control and D. I cheated a little bit. And on the side, basically, what I want you to do now is actually get some graphs. Okay. Now I didn't, obviously what I did was not correct, so let me go ahead, insert chart. We're going to do a scatter chart. And so basically what you're seeing is two lines. I would suggest you either do a chart with two axes, or what I actually like to do, I'm just going to copy the one and delete one of the lines in each. And in this case, I'll delete this. And so what you're seeing over here is your remaining UOD continue down, while your dissolved oxygen takes a dip and goes up. Now we can also just modify these. I like to modify so that my data series now, I know that I want to add a line. Excuse me. Marker style, line, come on, let's add that line there, marker style, automatic, no marker, so that's a line, and we'll do the same over here. It's modeled, so we're not looking specifically at data points, we're looking at the thing. So marker style, no marker, and line. And we're going to say add this color. So we're over here. So that's kind of cool now. What you can see, that's your bare bones StreeterPhelps model right here, you've got the remaining UOD dropping all the time, and you have that familiar sag curve that goes down. Your DO gets consumed, and at this point now, your the amount of BOD in the water is times the decay coefficient is less than the amount of re-aeration that's going on. So in fact, what happens is that your recovery actually goes up way above, and basically it's going to start to approach your saturated DO. So that's the basic StreeterPhelps model. It's unrealistic in the sense that you're always going to have sediment oxygen demand, and then also oxygen demand from your non-point source pollution that's coming in. The other thing, what I want to show you now is if we had to say, take this wastewater treatment plant and say it's zero, you'll see what happens now. There's zero stuff coming in from the wastewater treatment plant, and you'll see an immediate increase. So that's not really, not a truly realistic model, and we can play around with this now, and you can see that sorry, not 10, let's do, say, 40. You can see now what you need to do to get a characteristic sag curve going there. The next thing that we'll do is try and get a realistic situation, or at least simulate a realistic situation by adding sediment oxygen demand and non-point source UOD, so that assuming we didn't add any wastewater treatment, our DOs and our BODs would remain more or less in equilibrium. So that's going to be our next step. But for now, I think this will give you some food for thought. I'd like you to get your models here, and this will probably be part of a homework. It might be an additional assignment. I don't think it's a huge additional workload, but from here on it becomes a lot more fun, because then you start playing with your model, which is a lot more fun then. Well, if you build it, you're also enjoying some of the fruits of your labors as you start playing with it. Okay, thanks very much, and look forward to getting your homework back. And as I said, I'll let you know when that's due by.